Yes, same the guy. This is our part 2 of our discussion. Please don't forget to subscribe, like the video, and share. We are going to talk about how to draw the Lewis structure. We talk about the formal charge, concept of resonance, exceptions of the octate rule, which we discussed up here. Now, before discussing how to draw the Lewis structure, let's first discuss the formal charge, because we are going to see formal charges in our structures. What's a formal charge? What's a formal charge? Formal charge is the electrical charge difference between valence electrons in an isolated atom and the number of electrons assigned that atom in a Lewis structure. So it's the charge difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. Example, we have examples. First, we have, let's use carbon dioxide. How can we draw the Lewis structure for carbon dioxide? These are the steps. I've summarized them such that we can all follow. First step, we draw the skeletal structure of a compound using the chemical symbols, and we place the bonding atoms next to one another. Now, but the less electronegative atom is always in the middle. But for hydrogen and fluorine, they're always in the terminal position, because you can find that hydrogen can be more electronegative than some elements, yet it's in the peripheral part or terminal part. But here's the rule: hydrogen and fluorine, they're always in the terminal position. But here you have no hydrogen or fluorine. So carbon is less electronegative than the oxygen atoms, meaning that carbon will be in the middle. Then we place oxygen atoms surrounding this carbon atom. That's the first step. Second step, count the total number of valence electrons present in the molecule. So in this molecule, the valence electrons, the total number. Remember, oxygen is having 6 valence electrons. Carbon is having 4. But here we are having 2 oxygen, meaning that we times this by 2. We multiply it by 2. So, meaning that total number of electrons here we have 16. 12 plus 4. That's the total number of electrons in this molecule. We have statements here for polyatomic anions, we add charge value. Then for polyatomic cations, we subtract the charge value. But we shall see this in the next examples, because here we have no charged atoms. So next step, draw single covalent bonds between central atom and the surrounding atoms. Mean that we shall draw covalent bonds. We shall draw them. Now, next step, complete the octet of the surrounding atoms. This is the central atom. These are the surrounding atoms. Now, completing octet means that we make these surrounding atoms to be surrounded by 8 electrons, because we talked about the octet rule here in the first video. So, oxygen is having 6. So, it is having 1, 2, 3, 4, 5, and 6. But its octet, remember, in the bond, here we have 2 electrons. So, it is having 8, surrounded by 8 electrons. So also this one, 1, 2, 3, 4, 5, 6, 7, 8. So this is the next step to complete the octates of the surrounding atoms. But remember, in case of hydrogen, for it is stable when it is surrounded by only 2 electrons. Next step, lone pairs must be shown. Of course, we are showing the lone pairs, but we have to count the electrons. Are they 16? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're on that track. Now, but the central atom is not surrounded by 80 electrons. It's having 1, 2, 3, 4. So what's next? Try to add double or triple bonds between these atoms using the lone pairs of electrons from the surrounding atom to complete the octet of the central atom. So we want to complete the octet of the carbon, but we are going to use the lone pairs of electrons on the surrounding atoms. So we can use these to form a bond. Then it's having 1, 2, then 3, 4, 5, 6. So we use this one to make a bond. So carbon is surrounded by 80 electrons, and also oxygen is surrounded by 8 electrons, same as this oxygen. So mean that this is the Lewis structure for carbon dioxide. It is COO, but oxygen is having lone pairs of electrons. So if you try it another way, for example, you have this. When we follow the same procedure, you have this. Then we draw our bonds. You complete the octet of the oxygen. But carbon, its octet is not complete. So we use electrons to form a bond. I'm saying we can use this one again, form another bond. Mean that this one is having oxygen 1, 2 plus this 6. It is having 8. Carbon is having this 6 plus this 2 is also having 8. Also this oxygen is having 1, 2, 3, 4, 5, 6, 7, 8 is also having 8. Now, which structure is true? So here it comes the formal charge. In this structure, there is no negative charge or positive charge. We said formal charge is the electrical charge difference, the difference in electrical charge between a valence electron in an isolated atom and number of electrons assigned to that atom in a Lewis structure. Now, if you try to break this, if you try to break from here and also from here, you see this oxygen is having 1, 2, 3, 4. No, we are separating the electrons, mean that this one will take 1, even this one 1, 1 for each bond. So it's having 1, 2, 3, 4, 5. This oxygen is having 5 electrons, but normally oxygen is having 6. Mean that it is missing. It's missing an electron, so it will be plus. Then this carbon is having 1, 2, 3, 4. It's the same. Carbon is having 4 electrons. Then this oxygen is having 1, 2, 3, 4, 5, 6, 7. It is having, so it is minus, mean that it gained the charge. It is having 7 instead of 6. So this one is plus, this is minus. Now, this one, if you try to break it into like this, so this oxygen is having 1, 2, 3, 4, 5, 6, which is true. Even this one is having 6 normal electrons when it is isolated. This carbon is having 1, 2, 3, 4. So you see that this structure is more true than this structure, meaning that this is the true structure of carbon dioxide, not this one, which is having charges. So we go with the structure which may not have the charges. In case we have charges, we go with the least, with the one with the least charges. But if you have two, one with charge, another one without charges, go with the one without charges. Another example, we can have carbonate. First step, we said that we write the skeleton. So carbon will be in the middle because it is less electronegative. Then oxygen, we have 3 of them. Then we draw the bonds. After drawing the bonds, we complete the octates. Okay, before drawing these bonds, we say that we count the number of valence electrons present. This one, oxygen, we have 3 of them, meaning that it is 6 times 3 valence electrons, which is 18, plus carbon, which is having 4. Right? But we say that for polyatomic anion, we add charge value. Now, this is polyatomic and it is anion. Means that we add 2 to the total number of valence electrons. So, mean that we shall have 18 plus 4 plus 2, which is 24 electrons. So, we are going to use 24 electrons. Now, after getting this one, you draw the bonds. Then you complete the octates of the surrounding atoms. So, this is 1, 2. At every bond, you have 2 electrons. So, mean that we are adding 60 electrons for each oxygen atoms. For each oxygen atom. So, each oxygen atom is surrounded by 80 electrons, meaning that we have completed the octates of the surrounding atoms. But for carbon now here is having 1, 2, 3, 4, 5, 6. So we say that if this happens, we try to complete the octet of the carbon by using the lone pairs of electrons of the surrounding atoms. So I can use this one to draw a bond here. So this oxygen is having these 4 plus 4, which is 8. This one is having 8 and this one is 8. Then carbon is having 1, 2, 3, 4, 5, 6, 7, 8. So it's having 80 electrons surrounding it. But now, how can we put this minus 2? When you try to divide this like this oxygen is surrounded by 1, 2, 3, 4, 5, 6 plus 1 electron, which it contributed. Mean that it is having 7 electrons, but yet oxygen is supposed to have 6 valence electrons, but here in the structure is having 7. So it is 7 minus 6, meaning, okay, it is 6 minus 7. We take the valence electrons minus the electrons in the structure. So it is having -1. So we shall have minus on this oxygen. When you come to this one, is 1, 2, 3, 4, 5, 6. So it is already 6 minus 6, which is 0. So we have no charge on this oxygen atom. Then this one is surrounded by 8. I mean 7, because this is 1 plus this 6. So it is having a -1. Carbon is having 1, 2, 3, 4. So it is 4 and it is having 4 in the isolated atom. So this and this it's the reason why we are having a minus 2 here. So that's why it is a minus 2, because of these two charges. Another example, let's go to ammonia. Ammonium ion. This is polyatomic anion. Anion. This is polyatomic cation. Same rules. Nitrogen and hydrogens. We say that hydrogens, they always are the terminal position. Hydrogen and fluorine, they always at the terminal position. Means that this structure shall have this. We draw the skeleton. Then we count the total number of valence electrons. Nitrogen is having 5. Each hydrogens, we have 4 of them, each is having 5. So it is 1 times 5. I mean, there are 4, which is 1 times 4. So there are 4 electrons surrounded by these hydrogens. Then, since it's a cation, we say that for polyatomic cation, we subtract the charge value. So, this one, we have 5 plus 4, which is 9. So we subtract 1. So we shall have 80 electrons to use. So after this, next step is to draw single bonds for all of them. After drawing single bonds, you try to complete the octates of the surrounding atoms. So here, each hydrogen is supposed to have, we said for hydrogens, it is stable when surrounded by 2 electrons. Means that at each bond you're having 2 electrons. So each hydrogen is stable. But nitrogen, is it stable? Nitrogen, we are having 10. But it's having 1, 2, 3, 4, 5, 6, 7, 8. So it's surrounded by 80 electrons. Which is also stable now. Now, what's the charge? Here we are having plus a positive charge. Let's see. Hydrogen. If you try to break this bond like this, these bonds, mean that we are separating the bond electrons. Hydrogen will have 1. Each hydrogen is supposed to have 1 when it is isolated. So each hydrogen will have 1, 1, which is okay. Then nitrogen is having 1, 2, 3, 4 instead of 5. Instead of 5, it is having 4. We said we get the charge of the isolated atom, the number of electrons of the isolated atom minus the electrons surrounded by this atom in the Lewis structure, which is 5 minus 4, which is 1. And this one is positive. So that's why we're having a plus on ammonia, because of this nitrogen having 4 electrons instead of 5 electrons when it is isolated. So the structure of ammonia is this one without these lines. Don't put them. Don't put them. Let's have one more example. This time we are going to use ozone. This is the ozone. We are having 3 oxygen atoms. Of course, they have the same electronegativity. And so we follow the same procedure. First, we say that we draw the skeleton. So any oxygen can be anywhere because they are the same. They are having same electronegativity. Then next step, by counting the valence electrons of the atoms. Oxygen, you are having 3 of them, and each is having 6 valence electrons. So it is 6 times 3, which is 18. So In the structure, we should have 18 electrons. After this, we draw the single bonds connecting the atoms. Then we complete the octet of the surrounding atoms. After completing the octets of the surrounding atoms, we see, are we having the same number of electrons as we counted here? You're having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Instead of 18, you're having 16. So the remaining 2 are added to the central atom. The remaining 2 electrons. Next step, we look at the octet of the central atom. If it's not fulfilled, we get electrons using the lone pairs of electrons from the surrounding atom to form the bonds. We can use N of the oxygen. So we draw another bond to make the octet of the central atom complete. So it's having 1, 2, 3, 4, 5, 6, 7, 8. Also this one is having 8 and this one is having 8. Let's see the charge, the formal charges. If you try to isolate these atoms, this oxygen atom is surrounded by 1, 2, 3, 4, 5, 6, 7 electrons instead of 6. So we get the valence electrons for an atom when it's isolated minus the electrons which are surrounded by this atom in the Lewis structure. So it is 6 minus 7. So it is negative 1. So this oxygen, we shall put a minus charge. This is the formal charge for this oxygen atom. This one is having 1, 2, 3, 4, 5. It's having 5 instead of 6. So it is 6 minus 5. So it will have positive 1. So we put a plus. When it comes to this one, it's having 1, 2, 3, 4, 5, 6. So it is the same as the isolated oxygen atom. Meaning that ozone, this is its structure, the Lewis structure with formal charges included, but it is neutral. It has no net charges because the positive and negative charges are equal. So this is the structure with the charges, the formal charges for ozone. Now let's go to concept of resonance. Here we're having this structure, ozone. For concept of resonance, what is resonance first? What is resonance? Resonance, this is the use of 2 or more Lewis structures to represent a molecule which cannot be represented by only one Lewis structure. So it's the representation, or it's the use of 2 or more Lewis structures to represent a molecule which cannot be represented by only a single Lewis structure. We have this very example of the ozone. We say that we can borrow a bond from this oxygen, put it here. But at the same time, we can use this. And this bond, it's at this oxygen and this. It's in between these two, not this and this. So this one will be 1, 2, 3, 4, 5, 6 minus. Then this one have the lone pairs and a positive charge. This one is having 1. It's having 2 lone pairs of electrons. So these are the 2 resonance structures which can be drawn for ozone. So Ozone may not be represented by one structure because they are both correct. They are all possible structures. Another example, we have carbonate. Let's put it here. We have carbonate. Let's try to draw the structure of carbonate. It is C, put O, O, and O. How many electrons? We have 6 times 3, which is 18. Then we add for carbon, which is 4. Then we add the charges, the charge value, which is 2. Mean that we have 18 plus 4 plus 2, which is 24 electrons. Next step, we can put bonds to connect the atoms. Then we complete the octet of the surrounding atoms. Then from here, you can count. Are we having 24 electrons? This one is surrounded by 8. This one is also 8, and this one is 8. 8 times 3 is 24. So it is correct. We're having all the electrons. Then the octet for carbon is not fulfilled, so we can borrow electrons from one of the oxygen. Mean that we can draw from this one and complete the octet of the carbon. But at the same time, we can borrow from this one. Mean that we can draw this when the bond is here. And this bond like this. Now this one is having 2 like this. So again, we can use that same structure when the bond is here on this carbon. Like this. Like this. They are all possible structures. I haven't put the charges, but you can put the charges. So these are all resonance structures, and they are represented like this. Then we use double arrows. So those are the 3 possible resonance structures for the carbonate. Even this one, it's the same. We use the double arrow, but they should be like this one. So use double arrows to show that they are all possible structures. We can put the charges. Just try to put the charges. When we isolate these atoms, this one have a minus. Also this one have a minus. These two, they have no charges. Here we can have a minus and a minus here. This one, a minus and a minus here. So those are the possible ways. Let's go to the exceptions of the octet rules. Yes, exceptions of octet rule. Exceptions of octet rule. These are 3 where the octet rule doesn't apply. 1, we have incomplete octet. That's 1 we are going to see. Second, we have odd electron molecule. Then the third one, those with expanded octet. We have beryllium. It is an example. This beryllium, for example, if you have beryllium hydride, beryllium and hydrogen, if you try to draw the Lewis structure, beryllium has 2 valence electrons. Hydrogen is having 1 valence electron. But to be stable, we say that it needs only 2 electrons. So if you draw like this, we connect the atoms. The hydrogen is having 2, even this hydrogen is having 2 electrons. So this hydrogen, we said that it can be stable by 2, even this one is stable by 2. Then beryllium, we shall not complete the octet, so it is having only 4 electrons. So those are exceptions of octet rules. We say that octet rules mainly it's for period 2 elements, though there are some exceptions. For odd electron molecules, here we have an example. You can use the nitrogen monoxide. If you try to draw the Lewis structure, you have the nitrogen and oxygen. That's the first step. Electrons, nitrogen is having 5, oxygen is having 6. So, which makes the total of 11 electrons. So when we draw the bond, we complete the octet of the surrounding atom. Now it is oxygen, because nitrogen is less electronegative than oxygen. So this one is the surrounding atom, which is connected to nitrogen. Then from here, let's count the number of electrons. We're having 1, 2, 3, 4, 5, 6, 7, 8. So mean that we are remaining with how many electrons? Which is we are having 3 electrons remaining. 1, 2, 3. We put them. So oxygen and nitrogen, we can't complete the octet. If you try to complete the octet, if you put a double bond here, it's having 1, 2, 3, 4, 5, 6, 7. I'm saying again, if you try to put another bond, it is having these are 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can't complete its octet. Meaning that those ones with odd electron molecules, those odd electron molecules cannot be completed. Their octet cannot be completed. Let's try nitrogen dioxide. We're having nitrogen with 2 oxygen atoms. Total number of electrons, it is 6 times 2 plus 5, which is 17. So you draw the bonds, you complete the octets of the surrounding atoms. So here we're having 8 plus 8, which is 16, meaning that we are remaining with one electron. So that remaining electron is put to the central atom, which is nitrogen. Of course, you can't complete octet of nitrogen here because of this odd number of electron. Whenever you're adding 2 electrons, this one increases by 1. So we cannot have 8 electrons surrounding nitrogen. For expanded octets, an example, it is sulfur. For example, in sulfur, hexafluoride, sulfur is surrounded by 6 fluorine atoms. So we're having 1, 2, 3, 4, 5, 6. Then we draw bonds connecting these atoms. Remember, sulfur is having valence electrons, which are 6. Fluorine is having 7. Now they are 6. 7 times 6. So the total number of electrons, they are 48. Now, after drawing the bonds, you complete the octet of the surrounding atoms. So we are adding 6 since we are having already 2 here. to complete the octates. So we try to count the number of electrons here. See whether they are 48. So it is 8 at each part. So 8 times 6, we shall have 48. So meaning that the number of electrons we are having, they are the same as the one we counted. Meaning that this sulfur cannot be surrounded by 8 electrons because it is having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we say that octet rule is mainly for period 2 elements. And this sulfur is in period 3, meaning that it can have the orbitals. Because if you're having 1s, 2s, then 2p, 3s, 3p, and 3d. The maximum number of electrons here in the second period, they are 8. But the maximum number here can go up to, here it is 8. We add these ones, which are 10. So they are 18. Meaning that sulfur can expand its orbital. That's why it doesn't obey the octet rule. Yes, it's MK the guy. Thanks for watching. Please don't forget to subscribe, like the videos, and share. Thanks so much.